All right, so welcome to the fifth video in our covalent bond chapter. Again, going to follow along with your PowerPoint fairly closely. Today we are going to talk about how to determine what kind of bond something is. So if I give you NaCl, if I give you AsF5, how do you know what's happening to the electrons? What that's sometimes called is ionic character. Okay, and that's really just saying what kind of bond is it? Is it ionic? Is it covalent? And then there are some subdivisions we'll get to in a minute. So the number one way to do this is what we usually talk about doing in class, and that's just look at what elements are involved. For example, if it's a metal and a nonmetal, you know that's an ionic bond. You're transferring electrons. You know if it's two nonmetals or a nonmetal and hydrogen, that special guy, it is a covalent bond and they're sharing. So that's one pretty easy way. But the other way kind of helps you break it down even farther than just ionic versus covalent. And what that is looking at electronegativity. Now, you got to think back to learning this a couple units ago. Electronegativity is very simply how tightly that atom is holding its electrons. Okay? What is its tendency to really attract the electrons to itself? And if you remember the unit before, we talked about how it's pretty well influenced by how much positive charge there is in the nucleus, okay, so the number of protons, and electron shielding as we move down a group becomes a very big deal. So we learned that there was a periodic and a group trend with electronegativity. So if I look at the periodic table, okay, and I'll slide this up so you can see most of it, we talked about how electronegativity was going to be nice and high here in this top right-hand corner, got lower as we go down, lower as we go this way. Okay, so if you remember all that, that was way back when. So the way we look at what kind of bond it is based on electronegativity is we look at how big the difference is between the values. So your first option is we've got a big difference. A big difference means there is one atom that wants the electron and the other one, not so much. Okay, think about this as my one and only Chick-fil-A vanilla milkshake. Okay, if one of you out there really just doesn't like Chick-fil-A vanilla milkshakes and there's one sitting in between us, it goes to me. Okay, so this is me. This is the milkshake. I'm happy. This is you. You don't have a milkshake, but you're also happy because you really don't want it. If I'm getting the whole milkshake, that is an ionic bond. That is a transfer of electrons. And that happens when there is a big difference. I'm telling you, I'm mildly ratted when it comes to these things. I want the milkshake. So I'm getting it. You really don't care, so you're perfectly fine without it. Now, the way we look at this is by looking at values in the electronegativities. This periodic table is showing you electronegativity values. So instead of just showing you, hey, it's high here in this top corner, and then it's, high here in this top corner, and then it goes to low, I'm actually giving you numbers. If you look in each square, you will see there is a value for electronegativity. So if we have an electronegativity difference that is greater than 1.70. No, you don't need to memorize that. That's going to be an ionic bond. So if we look at, let's say, sodium chloride, we'll do an easy one. Sodium is 0.9, chlorine is 3.0. Okay? Chlorine wants those electrons. Sodium, as we've talked about, could care less. So the difference between 3.0 and 0.9 gives us 2.1. That's greater than 1.7. That's an ionic bond. That's how you can do this looking at electronegativity values. The other possibility is what if it's less than 1.7? Okay, if it's less than 1.7, okay, that's going to be kind of an equal attraction for electrons. Okay, and I'm going to put equal in quotes because I'm going to subdivide this in a second. If both of us kind of want the milkshake, and let's be honest, that could happen, that means that we're going to have to share and we're going to get a covalent bond because we are sharing the electrons. Nobody's willing to just hand over the milkshake, so there has to be sharing. But, as we all know, not all sharing is created equal. So if it's Coach Michael and I, there's me, there's him, And just for kicks, for those of you that have had him in class before, there's his red beard, okay? If this is the two of us and the milkshake is between us, all right, there's going to be kind of a medium difference. He likes these Chick-fil-A milkshakes, okay? I love them. So am I going to share? Yes. But my sharing involves, okay, here, honey, you can have one sip and now you're done. That's what happens when there's a medium difference between the electrons, okay? They are still sharing. It is absolutely sharing. I'm not taking the milkshake and keeping it all for myself. We are sharing. But it is an unequal sharing of electrons, okay? An unequal sharing. What the unequal sharing gives me is something called a polar covalent bond. And I got a couple pictures to show you that will help you with this. A polar covalent bond means the electrons are actually closer to one atom than they are another. They're not being 50-50 share. It's more of a 75-25 sharing. And that results, the reason we call it polar, in positive and negative poles or sides on our molecule. That's what we're talking about with this medium difference. So if we look at one of the easiest examples of this, okay, let's look at water. If you look at the electronegativity values that are on here, okay, we have H and O. Hydrogen, sorry about that, hydrogen is 2.1. Okay, there he is right there to 2.1. Oxygen's a 3.5. So if I do a little math here, 3.5 minus 2.1, that's a 1.4 difference. That's less than the 1.7, but that's still a pretty big number. So what we're seeing is that oxygen wants the electrons a lot more than hydrogen does. I'm oxygen, Coach Michael is hydrogen. And the result you get is that uneven sharing. This is what water really looks like. Okay, we learned already that it's bent, but what I really want you to see is look where these electrons are. Okay, those electrons are so much closer to to oxygen than they are to hydrogen. Okay, we're pulling those electrons in closer because oxygen has that much greater attraction. It's much more electronegative. That gives us these positive poles. Because think about it, hydrogen's not surrounded by electrons. These two are its electrons. So the nucleus is kind of out here by itself, giving these Mickey Mouse ears those positive charges. And then with these unshared pairs on this side, we have more of a negative charge. That is a polar covalent bond. It's an unequal sharing of electrons. What we sometimes see these molecules called are dipoles. Okay, and dipole is partially negative on one side, partially positive on the other. The other possibility is if we really don't have much of a difference at all. Okay, if you get a very small difference in your electronegativities, you are going to be sharing, but it's probably going to be an equal sharing or a somewhat equal. Okay, sometimes if it's a teeny tiny difference, it's not 100% equal, but it's close enough. If you have an equal sharing of electrons, it is called a non-polar covalent bond. And that non-polar covalent bond means there are no positive and negative poles. Okay, it's almost like, positive and negative poles is like a magnet. A non-polar is just like a piece of paper. There's nothing there that's kind of that magnetic attraction. So if we look at CH4, let's look at methane. We see we've got carbon and hydrogen. So if we look at our values, hydrogen 2.1, carbon is 2.5. That's only a 0.4% or 0.4 difference. Those numbers are so close together, they pretty much have almost an equal attraction. So what happens is they really do share their electrons equally. When I look at the methane molecule, and this is what you're looking at right here, you see this time the electrons are basically splitting the difference between the carbon and the hydrogen. They're not pulled closer to one side than they are the other. So each of these four bonds right here is called a non-polar covalent bond. And again, the easiest way to tell that is by electronegativities. Now, are you going to have to memorize electronegativities? Of course not. But you do need to understand the concept of those differences dictating what's going on. The other thing we can do with this is we can look at a molecule as a whole and decide, is this molecule polar or is it nonpolar? Okay, easiest way to do that, there's a couple, one of which is going to be just look at the polarity of each bond. For example, if all of the bonds that you have are nonpolar, then, wait for it, the molecule is nonpolar. Okay, so think about the one we were just looking at, all right? CH4. Everything in there is nonpolar, therefore that's a nonpolar molecule. The other thing you can do is you can look at the overall shape. What you're looking here is symmetry, okay? If you have polar bonds that are all symmetrical, they will essentially cancel each other out. So if we look at carbon dioxide, for example, carbon and oxygen, these are polar bonds. These double bonds right here, okay, these are polar bonds. But because they're symmetrical, okay, they essentially cancel each other out. So where you would have a positive side and a negative side, okay, they're so symmetrical that it just cancels everything out, and this becomes a non-polar molecule, okay? If you have non-symmetrical polar bonds, so think about water, okay? With water, we know I've got that bent shape, and we've got these extra electrons. Okay, this is not perfectly symmetrical, and I know some of you art people are going, yes it is, look at that. But you've got to think about it kind of in 3 dimensions here, so you have to also consider what's going on at the top and the bottom. Since they're non-symmetrical, this becomes a polar molecule. The last thing we talk about with this whole polarity thing is we talk about attractions between molecules. So really what we're talking about here is intermolecular forces. So couple that you need to remember. One is called hydrogen bonding. Hydrogen bonding is exactly what you think it is. It's a hydrogen from one atom bonding to the negative or the electronegative part of another. This is a crazy strong intermolecular force. Okay, it's really strong. It's the strongest one we have. And lots of times you see fluorine, nitrogen, and oxygen involved in this. When you look at the picture, you can see kind of how this is indicated, all right? They've got all these little symbols, don't worry about these, but you can see what's happening with this hydrogen bond is you've got the positive over here attracted to the negative over here, and it's a hydrogen that's the positive charge and something else that's electronegative. This one happens to be oxygen, which is one of the very common ones. This is why you can float. Water molecules have very, very strong hydrogen bonds between them. Another intermolecular force is something called a van der Waals. Yes, these are real words. Sorry about my lovely handwriting. A van der Waals force, or sometimes it's called a London dispersion force. What this is, it's a very weak attraction between atoms that's caused by the negative electrons on one side being attracted to the nucleus of the other. So picture these as 2 different nuclei. All right, here's my little electron levels. And as you guys know, the little electrons are cruising around, okay? They're in constant motion. So what a van der Waals or a London dispersion force is it's a very, very weak attraction. When this negative electron gets over here, he is all of a sudden attracted to this positive nucleus right here. But the electron doesn't stop moving. So as soon as he keeps going the other direction, yeah, now he's not attracted anymore. When he comes back around again, ooh, I'm attracted. Now that I keep going, yeah, not attracted anymore. It's a constantly changing force, but it does exist. So that's another one for you guys to know about. So when we put all this information together about polarity and, covalent bonds and sharing electrons, we get kind of the overall properties of these kinds of compounds. So covalently bonded compounds are pretty poor conductors of heat and electricity. Okay? Because they're not willing to give up those electrons, they're just not able to conduct very well. Because their molecular forces tend to be weaker, we see them usually as liquids and gases. Now that's not always true, obviously, but it's true a lot of the times. Think water, think carbon dioxide. And again, the reason we see that is the weaker attraction between the atoms. Those ionics, when you are donating a kidney or an electron, that's a really strong bond. Dude, we're holding hands when we're sharing electrons. I can break that pretty much easily. So because I can break it so easily, we will see low melting points and low boiling points. Okay, so one of the biggest things you guys need to do is you need to practice ionic and covalent. You need to be able to have NaCl, Fe2O3, okay, CS2, what's a good one I'll put on you? Forget that H. We'll do SiH4. And you need to be able to name these, which means you've got to be able to think, is it ionic or is it covalent? And that's a big thing we're going to go over in class, so make sure you catch up with that.